Imagine shrinking yourself down billions of times until you could see the inside of an atom. Most people picture the same scene: a dense nucleus at the center and tiny electrons flying around it like miniature balls. The electron in this picture is simply a very small particle, like a grain of sand, too tiny to see. It has a definite position, a clear boundary, and moves through space the way any object does. This idea feels natural because our everyday experience is built around particles. Throw a stone and it follows a path. Drop a grain of dust and it falls. Every object we interact with behaves like a small piece of matter moving from one place to another. So, when scientists first discovered the electron in 1897 through the work of J.J. Thomson, it was almost inevitable that they imagined it the same way, as a tiny charged particle moving through space. For years, that interpretation seemed perfectly reasonable. Experiments showed that electrons had mass, electric charge, and could be deflected by electric and magnetic fields. These are exactly the properties we expect from particles. The evidence appeared to confirm the simple picture of electrons as miniature objects. But as scientists pushed deeper into the microscopic world, strange things began to happen. Experiments started revealing behaviors that no ordinary particle could possibly exhibit. Electrons seemed to pass through barriers they should not cross. They produced patterns that looked like ripples spreading across water. Sometimes they behaved as if they existed in multiple places at once. The deeper physicists investigated, the more the simple particle idea began to break down. Electrons did not behave like tiny balls moving along predictable paths. Instead, they acted in ways that seemed to contradict the very definition of a particle. One experiment in particular would force scientists to confront an unsettling possibility. Electrons might not be particles at all. They might be something far stranger, entities that blur the line between objects and waves, existing in a form that our everyday intuition was never designed to understand. The first serious crack in the electron as a tiny particle idea came from one of the most famous experiments in physics, the double slit experiment. At its core, the setup is surprisingly simple. Imagine a barrier with two narrow openings cut into it, and behind that barrier is a screen that records where incoming objects land. If you fire small particles, like tiny beads, toward the barrier, each particle must pass through either the left slit or the right slit before hitting the screen. If electrons were ordinary particles, we would expect them to behave the same way. Over time, the screen should show two bright stripes corresponding to the two slits, because electrons would simply pass through one opening or the other. But that is not what happens. When scientists perform this experiment with electrons, the pattern on the screen does not form two stripes. Instead, it forms a complex series of bright and dark bands known as an interference pattern. This is exactly the pattern created when waves overlap like ripples spreading across water and interacting with each other. This result suggests something extraordinary. The electrons are behaving like waves. Even more astonishing is what happens when scientists fire electrons one at a time. If electrons were particles, each one should pass through a single slit and land somewhere behind it. But even when they are sent individually, the interference pattern gradually appears on the screen. That means each electron somehow behaves like a wave passing through both slits simultaneously. The situation becomes even stranger when researchers attempt to observe which slit the electron actually passes through. The moment detectors are placed near the slits to measure the electron's path, the interference pattern disappears. Instead of wave-like behavior, the electrons suddenly act like ordinary particles again, producing two simple stripes. In other words, the electron's behavior changes depending on whether it is being observed. This experiment shattered the classical picture of electrons as tiny solid objects moving along definite paths. A particle cannot travel through two openings at once. A particle cannot interfere with itself like a wave. And a particle's behavior should not depend on whether someone is measuring it. Yet electrons do all of these things. The double slit experiment forced physicists to accept an uncomfortable truth. Electrons cannot be described purely as particles. Something deeper and more mysterious is happening at the quantum level. Something that challenges our most basic assumptions about what matter really is. After the shock of the double slit experiment, physicists faced a difficult question. If electrons are not behaving like particles, what exactly are they? The first clue came from a bold proposal by the physicist Louis de Broglie in the 1920s. De Broglie suggested something revolutionary. If light, which was traditionally thought of as a wave, can sometimes behave like a particle, then maybe matter can behave like waves as well, according to his idea. Every particle of matter, including electrons, has a wavelength associated with it. This concept became known as wave-particle duality. In simple terms, it means that electrons cannot be classified as purely particles or purely waves. They possess properties of both, depending on how they are observed. When electrons interact with detectors or leave marks on a screen, they appear as localized impacts, much like particles. But while traveling through space, they behave like waves spreading out and interfering with themselves. This dual nature explains the mysterious results of the double slit experiment. The electron is not a tiny ball choosing one slit or the other. Instead, its wave-like nature allows it to spread out and pass through both slits at once, creating an interference pattern. But this explanation raises an even deeper puzzle. If the electron is a wave while traveling, what exactly is waving? In water waves, it is the water that moves up and down. In sound waves, it is the vibration of air molecules. But an electron wave does not ripple through any material substance. Instead, the wave represents something abstract, a distribution of possibilities. The electron's wave describes the probability of finding the electron in different locations. Before measurement, the electron does not have a single definite position. It exists in a spread-out state where multiple outcomes are possible. When a measurement occurs, that spread of possibilities suddenly produces one specific result. The electron appears at a single point, leaving behind the familiar particle like trace. This strange combination of behaviors forced scientists to abandon the classical categories of particle and wave. Electrons do not fit neatly into either description. They exist in a quantum state that only sometimes reveals particle-like properties. To describe this behavior properly, physicists needed a new mathematical language, one that could capture the full range of possibilities hidden inside the quantum world. That language arrived through a powerful idea known as the wave function. To make sense of electrons behaving both like waves and particles, physicists needed a new way to describe what an electron actually is. That description came from the work of Erwin Schrödinger, who developed one of the central ideas of quantum mechanics, the wave function. The wave function is not a physical wave like water or sound. It is a mathematical object that describes all the possible places an electron could appear. Instead of telling us exactly where the electron is, the wave function tells us the probability of finding it in different locations. In other words, before we measure an electron, it does not exist at one precise point. It exists as a spread of possibilities across space. Imagine a thick fog surrounding a mountain. You cannot see individual droplets moving along fixed paths. Instead, you see a cloud that fills an entire region. The electron behaves in a similar way. Around an atomic nucleus, the electron forms a probability cloud where it is more likely to appear in some areas than others. These regions are known as orbitals. Unlike the circular orbits shown in old atomic diagrams, orbitals are three-dimensional shapes representing where an electron is most likely to be detected. Some orbitals form spheres around the nucleus. Others stretch into dumbbell shapes or complex patterns that look almost like flowers. But the most surprising part of the wave function appears when a measurement occurs. Before observation, the electron exists in a spread-out wave-like state. But when an experiment detects the electron, the wave function suddenly produces a single outcome. The electron appears at one specific location on a detector screen. Physicists often describe this process as the collapse of the wave function. A cloud of possibilities reduces to a single event the moment measurement takes place. This does not mean the electron was secretly sitting at that position the whole time. Quantum experiments show that the spread-out wave truly represents the electron's physical state before detection. The act of measurement forces the system to choose one of the many possible outcomes. This is why electrons sometimes appear like particles. When we observe them, they produce localized impacts, giving the impression of tiny objects. But between measurements, the electron behaves like a wave of probability spread across space. The wave function therefore reveals something profound about the nature of reality. At the deepest level, matter is not made from tiny solid pieces moving along precise paths. Instead, it is described by patterns of probability that only become definite when we interact with them. To understand what an electron truly is, we must go even deeper beyond particles and waves to the modern framework physicists use to describe the fundamental structure of the universe. If electrons are not truly particles and not truly waves, then what are they? Modern physics offers an answer that is even stranger than anything proposed before. According to the framework known as quantum field theory, the fundamental ingredients of reality are not particles at all. Instead, the universe is filled with invisible fields that exist everywhere in space. A field is something that has a value at every point in space. For example, temperature can form a field across a room, and gravity forms a field around massive objects. Quantum field theory suggests that every type of particle corresponds to its own fundamental field, permeating the universe. Electrons come from the electron field. This field is present everywhere in space, even in what we call empty vacuum. An electron is not a tiny object flying through space like a miniature ball. It is a small excitation, a localized vibration in the electron field. A helpful analogy is the surface of a calm lake. The water itself represents the field. If a ripple forms on the surface, the ripple is not separate from the water. It is simply a temporary disturbance moving through it. In the same way, an electron is a ripple traveling through the electron field. This idea explains why electrons sometimes behave like waves. A ripple naturally spreads and interferes with other ripples. It also explains why electrons sometimes appear as particles. When the ripple interacts with a detector, the energy becomes concentrated at a single point, producing a particle-like event. So the electron is not a solid object at all. It is a pattern of energy moving through an underlying field that fills the entire universe. This realization changes how we think about matter itself. The atoms that make up your body, the air you breathe, and the stars in the sky are not built from tiny solid pieces. They are made from organized patterns of vibrating fields. What we call particles are simply the smallest measurable disturbances within those fields. At the deepest level, reality is not made of little objects, but of dynamic structures constantly fluctuating within invisible quantum fields. Electrons are just one example of these structures' stable patterns that appear particle-like when measured but behave like waves while evolving through space. So when we say an electron is not a particle, we are pointing toward a deeper truth. The universe is far stranger than our everyday intuition suggests. Matter is not made of solid pieces at all. It is made of ripples in the invisible fields that fill the cosmos.